All right, so that's kind of the basics. Um, what we're doing when we're graphing, these graphs can really look like anything. We can have really as many vertical asymptotes as we want. We're restricted on horizontal asymptotes to having really one or none. And then our graphs usually look something like this. But the problem is, it's not actually restricted to that. Sometimes in the middle of this, we can actually have graphs that pass through our asymptotes. Our asymptotes really, as far as a horizontal asymptote, it deals more with end behavior than with what happens in the middle. So in the middle, our graph can pass through it. But on the outside, what happens is our graph gets closer and closer and closer and closer to it. Now, vertical asymptotes, you can't pass through those. Our graph will never equal those. But we can have functions that have no vertical asymptotes, even though that they're fractions. And we can have weird looking graphs that look like this. And all of these come from polynomial functions from the top and the bottom. So that's what we're talking about with rational functions. F of x, where it's made up of two polynomials, where one polynomial is dividing the other polynomial. And we get all kinds of bizarre graphs. Okay, we can have graphs that we have things called slant asymptotes, where our graph may go like this. So we're going to talk about all those types of things. We're going to talk about removable discontinuities, where maybe we have not a asymptote, but we have a hole in the graph. So that's kind of where we're going with all of this. Again, we're not going to actually be graphing. We're going to just be finding all of these weird things. All right, so let's start with the rules for our horizontal asymptotes. A horizontal, as far as rule goes, it has the most complicated rule. Your book actually gives it to you as 3 rules to memorize. I try to give it to you as 1 rule. What you do is you choose the largest degree from your two polynomials. And we're going to let that degree equal n. So your asymptote is your coefficient of x of n on the top and your coefficient from x of n on the bottom. So that's where you get your asymptote from. No. Okay. Here. This one comes from g of x. This one comes from h of x. Okay, so let's say I had that for a polynomial. Okay. What is my highest power? 3. Okay. What is the coefficient of x cubed on the top? 3. What is the coefficient of x cubed on the bottom? 6. So, my asymptote occurs at y equals 1/2. That's all there is to it. I know it's a lot of explanation for something that's that simple. Remember, your book has it broken up into 3 rules. There's a reason why it's broken into 3 rules. And there's a reason why I had to write it out so complicated. Okay, for this one, what is my largest power? 3. Okay, what is the coefficient of x cubed on the bottom? 1. What is the coefficient of x cubed on the top? 0. So my asymptote occurs at 0.
Wait, why is it 0 over 1?
On the top, so this is my power. This is my largest power, right?
Yes.
Where's your x cubed on the top?
There is
There isn't one. So we have to add 1. But if I add 1, I can't change it, so I have to put a 0 in front of it. Yeah. We'll do that. So does it make sense, Manny? If there isn't one, you have to add it, but in order to add it, you have to put a 0 in front of it.
Okay, so it would be off the largest power.
Off the largest power. So we have to pick the largest power, and whatever that largest power is, we have to use that power in the top and the bottom. Okay, now, this is what Taylor was asking about, which is your third type. Okay, what's my largest power? X squared. What's the number in front of x squared on the top? What's the number in front of x squared on the bottom? Okay, so that's how I take their three rules. The way the book presents it is, if your powers match, then your asymptote is equal to the coefficient of both powers. If your asymptote is smaller on the top, then, or if your power is smaller on the top, then your asymptote is equal to 0. If your power is smaller on the bottom, then you do not have an asymptote. So they give it to you as three rules. I try to give it to you as one rule where you choose your largest power and then you use the coefficients of them. And if you don't have the power, then you just use 0 for your coefficient. Yeah? Go. Maybe 5/4. Or you mean power or number? Yep. So your coefficient needs to be a 5/4. So for horizontal, we either have one asymptote or no asymptotes. We can never have more than one. All right, any questions over horizontal? Now, in the case of no asymptote, funny things happen, but we'll cover that in a little bit. Okay, vertical asymptotes. Vertical asymptotes require more work, but the rule is really easy. For vertical asymptotes, they occur whenever your denominator equals 0. What did I use for the top? G of x? Yeah. So vertical asymptotes just happen whenever your denominator equals 0, right? We can't have a denominator that equals 0. So that's what happens that causes vertical asymptotes. So it's just that simple. Now, it takes more work because that means you have to do your factoring and everything else to find them. But the rule is easy. All right, so now I have several examples to show you what is actually required of you for your homework. All right, so for example 1. Let's see, let's start with horizontal. Okay, my largest power is 2. So what's the coefficient of x squared on the top? 0, because there isn't one. And on the bottom, 1. So my horizontal asymptote happens at 0. Okay, vertical asymptotes. I just need to take the denominator and set it equal to 0. All right, you can either factor or isolate the square, either one. Okay, now it's going to ask you to graph. I want you to graph, but whenever I ask you to graph, what I'm going to request that you do is draw in the asymptotes. Let's see, 1, 2, 1, 2. And then just give me a guess of what you think it looks like. I want you to guess. The guessing part is just for fun. Don't care. Whatever you want. It is just for fun. I want you to have something. I'm going to ask you to hold on to these so whenever we do this again later and you actually graph them on a graphing calculator, you can see how close you were. This is what the actual graph looks like. So see, this one actually passes through the asymptote in the middle. And if you want to get close on your guess, you can kind of pick a point in each section, so you can be in the right quadrant. I can choose a point out here so that I know whether I'm positive or negative. Pick a point in here. Pick a point in here. But I wouldn't grade you on it, which I'm not grading you on it anyway. The point of it is, so I'm going to have you do this homework again with a graphing calculator later. The point of this is so that when you're doing it with a graphing calculator, you can see how close you were. Again, this is just for fun. All right, this one. What I would grade you on the test is your asymptotes. That's the part I'm concerned about right now. Okay, largest power is x squared. So coefficient of x squared on the top is 2, on the bottom is 1. So my asymptote is going to occur at 2. Okay, my vertical asymptotes. You factor it, 2 numbers that multiply to 6 and add to 5 are going to be 2 and 3. So I'm going to have -2 and -3. Okay, this is basically the same sort of thing. I'm just going to guess the same sort of graph. Come on, you stupid calculator. Oh, I went the wrong direction. I tried these out all beforehand. I thought maybe I would remember. The parabola is down at the bottom. So it goes up at the top, and then there's a little parabola down at the bottom. Okay, this one. Horizontal. Okay, my largest power is 3. So there's a 1 in front of it on top. There's not an x cubed on the bottom. So I don't have one. Vertical. That's going to happen at 3. So that's what I have. So I'll let you guess on that one. Okay, there's that what that one looks like. So that's what a graph with no horizontal asymptote looks weird. Okay, removable discontinuity. Now, discontinuity is a fancy word for what's happening here. These are discontinuities. Discontinuities are places in your graph where if you were tracing it, you would have to pick up your pencil. So, whenever we were talking about parabolas, we were talking, or not parabolas, but polynomials, we were talking about how polynomials were continuous. Well, these are not continuous. These have discontinuities. So, an asymptote is one kind of discontinuity. A removable discontinuity is another type. All it is it's a hole in your graph. So, our graph is going along all nice and pretty. And then we have a spot where we can't graph. That's a removable discontinuity. So, it was supposed to be a vertical asymptote, but instead we were able to get rid of it. So now all we have is a hole. The way we get rid of it is by factoring. We factor our stuff, and then we remove our discontinuity. We remove that 0 from the bottom. We can't remove it all the way because we have to graph our original equation. That's why the hole is still there. Because we're not graphing just this. We still have to factor this into our graph. Which is one of the reasons why I'm having you guess at your graph, because you have to have some way of showing a hole. So that's one of the reasons why we're playing at graphing, so we can show a hole. Alright, so if we're doing this one, so every time you graph these, you have to try to factor. Now, the reason why we weren't doing that on the previous ones is because they weren't factorable. At least I made the numerators so they weren't factorable. Except for the previous one, but I already knew that it wasn't going to work, so. Okay, so I factor that. Those two cancel out. So now, whenever I'm going and I'm finding my asymptotes, horizontal is at 1. Vertical is going to be at -4. And I have a removable now at 3. So what I'm going to do is I'm going to guess at the way this graph looks. And then whenever I reach 3, what I'm going to do is I'm going to put an open circle to show that there's a hole there. Now, this is one of the reasons why we're doing this by hand, even though we're not graphing it all the way by hand. But you have to know some of this stuff before you just do it by calculator. Because your calculator, I drew it upside down. Your calculator doesn't show the removable discontinuity. It doesn't show that there's a hole there. So that's why you have to know some of this stuff before you go using your graphing calculators. Now, your calculator knows that there's a hole there, because if I go and try to calculate that, if I try to calculate what the value is at x equals 3, it tells me that there isn't one, but it doesn't show up as a hole on your graph because it can't show me that. So we have to be smarter than our calculators. All right, slant asymptotes. Last one. They only happen if the degree of g of x is 1 greater than the degree of h of x. Now, first of all, that means, if you look at example 5 is like that. First of all, that means that there's no horizontal asymptote. Because if I was trying to do horizontal asymptote of this one, my largest power is x cubed, so on the top there's a 3, on the bottom there's a 0. So in order to have a slant asymptote, we cannot have a horizontal asymptote. So if you have a horizontal asymptote, you never have to worry about a slant asymptote. It only occurs if there's no horizontal. And it only occurs if this power is 1 greater than this power. Not 2 greater. So on this one here, I set this one up so I wouldn't have to worry about slant asymptote. So I did that intentionally. Okay, what you do to find it, you take g of x divided by h of x equals, we'll call it q of x, plus your remainder. Q of x is your slant asymptote. You throw away your remainder. Huh? I'll show you. We'll do the example. Okay, so on this one, horizontal, none. Vertical, x squared plus 3 equals 0. X squared equals negative 3, so I get plus or minus I square root of 3, which means none, because I can't graph that. Okay, so I have to try my slant. So, yeah, since this is an x squared, I cannot use, my mind just went blank. Not long division, synthetic, thank you. I have to use long division, I can't use synthetic division. So, long division, I have to fill in any missing numbers with zeros. Alright, so what do I need to multiply x squared by to get 3x cubed? 3x. Okay, so that's 3x cubed plus 0x squared plus 9x. Subtract that. So I get x squared minus 14x plus 2. Okay, I just need a 1 to get x squared. Subtract that. So negative 14x minus 1. And then my remainder would be negative 14x minus 1 over x squared plus 3. So what we do is we throw away your remainder. So my slant asymptote is y equals 3x plus 1. Okay, so what I need to do is just graph that line. So y-intercept is 1, go up 3 over 1. And then I have no horizontal or vertical asymptote, so your guess is as good as mine what that one looks like. So go ahead and guess. Here's what it looks like. It follows the line, then it goes through it, kind of like in an x cubed fashion, and then it follows the line back up. So it's kind of going like this.
If there's an imaginary vertical, that means it's none.
Yeah, you can't, because you can't graph. I mean, graph I